Okay, so there we go. So tangent velocity is where we're at right now with our notes. We were a little bit behind, so let's see how much we can get through, because I need us to get caught up with Tuesday, Thursday students. It says here, since it's difficult to describe the motion of an object moving in a circle using linear terms, like we did last semester, circular motion is described in terms of what we call angles. The exception, though, is that even though we use theta or angles, our angles are not degrees. Last semester, when we were going up and to the right, we formed a right triangle and we used degrees to find the theta. This unit, when we are talking about circles, one more time, when you are looking at circles, we are not looking at degrees, we are looking at angles and what we call rads, okay? So, which through the object moves. Remember, we can do this based on that experiment that we did with the paper plate and the radians. The distance moved around the circumference of the circle when compared to the length of the radius will always be a certain angle, and we call that a rad. Now, I've got my paper plate over here, and on my paper plate that I did, because I know I have y'all's, so I can grade it, my paper plate has 1, 2, 3, 4, 5, 6 rads, 2 of them which are a little extra, but if you go and look at it, 57, 57, 57. 3 of them, 58, 58, and then 56. To have 3 of them that are exactly the same 57, that's pretty good. To be honest, though, remember what I said? They all should be the same. They should have all been the same degrees. But we're humans. The actual degrees, 57.3 degrees. 57.3 is the true number of every rad for any size circle. Doesn't matter if it's a small one, big one, medium one. It's always going to be 57.3. So for those of us who got that 57 or that 58 or even 56, you are awesome because you are so close. You're like really good.
54.
Okay, you're off. I was about to say awful. I was like off. Okay, but all angles in this chapter are going to be measured in what the terms that we call a radian, but which is not degrees. It's comparable to degrees. It's just like if I say we're going to talk about money in dollar bills or we're going to talk about it in coins. I mean, it's still money and they're still the equal amounts. Just like if I was to say 4 quarters equals $1. It's still, quote unquote, worth $1, okay? But it's just in 2 different forms. Here, we have radians, which are still degrees or angles, but instead of saying it like this, 4 quarters, we're saying $1 bill, okay? Or 1 piece of the pie, or 1 radian, okay? So that's where in your calculator, and you go to mode, and I want to pause for a moment to make sure, for those of us who had pre-cal already, or if you're in pre-cal, your teachers may have talked to you about this. We talked about this already last semester. When you go to mode, remember last semester we had to go down and look at that. Oh, snap. I'm still in degrees. Blue, what is this one that's flashing? Radian. There you go. Because degrees and radians are the same thing. That's like me doing my calculations with coins / dollar bills. Okay? So I need to come over here to radians, hit enter, and then clear so that way I can do my math. Okay? So radians is what we want to be in because that's how we talk about our circles when we're looking at the theta. Circular angle, though, it says over here, it's on this side. Circular angular speed is the rate at which an object rotates about the axis. Now, the speed and direction of an object moving in a circle is called tangent velocity. Look at that. Speed and direction, tangent velocity. There goes that velocity again when it comes to direction. Tangential velocity. But in math class, you might have used the word tangent, a tangent line off the circle, right? So you might have used that form of the word. This is because it says here, the direction is always changing to the circle or in that circle to form the circle. So to create a circle at every given spot, this spot, this spot, this spot, this spot, this spot, every single spot, it has to change its direction. If it doesn't change its direction, then it's going to shoot straight out in what we call a tangent line. Objects moving in a uniform circular motion will have a constant speed. But does this mean that they have a constant velocity? No. Why is that? No, because speed is a scalar, like last semester, and velocity is a vector quantity. And velocity not only has magnitude, but it also has direction. But very similar like we did last semester, even though we were talking about speed/velocity, we use those two equations interchangeable because it was d over t. It's pretty much the same thing over here for circles, even though they may use the word velocity or they may use the word counterclockwise or clockwise, which is the direction of the circle. We can still use the equation velocity or the speed equation because it's still kind of the same thing, just like last semester. It says here, so while the magnitude of the velocity vector may be constant, kind of like those carousel rides that move at a slow, constant speed, right? The direction for that ride, as it's moving at a constant slow speed, the direction is continuously changing so it can form that circle. And that direction of the velocity vector that is continuously changing is what we call a tangent line. Now, in math class, you might have used the word tangent. The word tangential is the same thing, so however you pronounce it. Tangential is the direction of the velocity vector at any instant, it says here, of that direction drawn in a straight line touching the circle, but does not go through the circle. It touches the edge of the circle, but it does not go through the circle. Again, I have no clue what kind of math skills you have or who your teacher was, if you had even had a chance to talk about tangent velocity. But if this circle is moving in this direction, I can see that through those arrows. Imagine if something was to break loose at this point, it would shoot out in what we call a tangent line. If it was to break loose at this direction or this location, it would shoot out at a tangent line. At this location, it would shoot out again in what we call a straight tangent line. That tangent line touches it, but it doesn't intersect it. Truly, the tangent line right here goes this one. The tangent line right here actually goes like this. It touches the edge of the circle, but it doesn't intersect through it, okay? It says here, let's just kind of go and summarize stuff up just a little bit. An object moving in a uniform circular motion, if I bring it down, would that be? Uniform circular motion is moving around the perimeter of that circle with a constant speed, which makes sense. It's not speeding up, it's not slowing down, it's on cruise control. But while that speed of the object is constant, the velocity is changing, parentheses, because direction is changing. The direction's always directed tangent to that circle, which is a line that touches it but does not intersect it. And at every given location of the circle, it is a new direction, so that way it can form a circle. If it's not, then it's not going to form a perfect circle. So they said, let's look over here. There's this tube that's placed on the ground, but they actually took out one little section of the tube, and they shot a golf ball through this tube. The golf ball goes, and it tells me right here, in. So it's going in this way. It's going around the tube, around the tube, around the tube. The question asks you, where is the ball? And when it falls out, where is it going to go? What direction is it going to go? Well, it's going to move in a tangent line. A tangent line would be a straight line like that. So at this location, if this was missing, it's going to move in a straight line. Same thing over here. You got to watch out if you're, I don't know, I've never been to race cars, but if for some reason a race car loses control and it's this one right here and he's moving forward in this direction, he loses his, I don't know, direction and he skids off, he's going to go in a straight line. Same thing for this one. He would shoot off in a straight line. So those people in the crowd need to be careful because that stuff is going to be flying at them, or the car is going to be flying at them. Imagine if I had a yo-yo and I was spinning it around and I was spinning it this way. If I was spinning it this way, most of us over here would be like, whoa, whoa. Why? Because if that yo-yo was to detach from the string at this location, it would shoot off in a straight line. At this location, what about if it's, here's my circle, and if it was to release here, it would go straight down. What if it was to release at this location, and it's moving this way, it would go straight up. So it would shoot off, and that's what the word tangent is telling us. That's it. Next one. Now from that tangent line, we actually have 3 different equations you could use. They all work. It does not matter which one you use. You can use number 1, number 2, or number 3. Either or. So let's look at this one. Number 1, let me go ahead and give this to you. V sub t equals 2 pi r over capital T. Tangent velocity equals 2 pi radius divided by period. That's what this equation is saying. Or you can use this one over here. Omega equals theta over lowercase t. Omega equals the theta divided by time. That's, a Greek letter. The last one that you could use is tangent velocity equals radius times omega. Omega looks like a W. It's not. It's a Greek letter from the alphabet. Okay? Now let's go back and let's fill all this stuff in to make sure that we're all on the same page. V sub t is tangent velocity. And because we use the word velocity, just like we did last semester, it's meters per second. Lowercase r is just like you had in math class. It's going to be radius, which is in meters. Capital T stands for period, which we already did in our notes, which is in seconds. And remember, if they give you frequency, you have to calculate the period. If they don't give you frequency, then that means you're going to have to figure out period on your own. The next equation, this little weird W, is angular speed. It stands for angular speed. Now, this little weird W right here is an omega symbol, but it's actually a lowercase omega symbol. Later on this semester, we're going to use an uppercase omega symbol, which looks like this. That's a capital omega. Lowercase, capital omega. Lowercase omega stands for angular speed. Capital omega stands for ohms. Ohms with electricity. Now, it uses the word speed here, but it also uses the word angular. And how do we measure angles for circles in physics? With rads. So this is a rad per second. The theta is angular displacement, meaning how much did you move around that circle? That is just a rad, not degrees. And a lowercase t stands for time, which is in seconds. The last equation, v sub t, is the same tangent velocity, but they're just using it a different way. Tangent velocity, which is meters per second, is the radius times the angular speed. Radius is in meters. Angular speed is rad per second. All right, so we got equation number 7, 8, 9 out of the way. Whew. And we're going to get a little bit further so that way we can get to the same point as everybody else. Here we go, examples. So it says here, let's look at the example, a couple of problems they gave us. A car is driving around a perfect circle. Now, it's 5 meters from the center, which means that's the radius. If they said that the circle was 5 meters across, that would be the diameter. You would divide it by 2. It completes 3 laps in 60 seconds. This is the time, and this is the turns. First question, or question number 1, is, well, what's the radius? 5 meters. What's the period? Well,
60/3?
Yep. Because I don't have frequency, I'm going to use the equation time over turns, or like Emilia said, 60/3, which equals 20 seconds. What is the tangent velocity of the car?
You can do the number 7 equation.
I can do number 7 equation. I agree with her. VT is 2 pi r over capital T. Your calculators have a pi button, or if you want to, you're more than welcome to push in the 3.14, either way. So 2 times pi times a radius of 5 divided by 20 equals my answer of about 1.57 meters per second, give or take. 1.57 meters per second. So, first thing, before we go any further, this is going to be the question they're going to give you on the test. Well, what's the tangent velocity of this car that's going around the track? They could do a couple of things. Number 1, what if they give this to you in kilometers? You got to convert it to meters. What if they give this to you in what we call diameter, all the way across? Because they're going to say the whole half, or the across the whole track is 10 meters. Then that means that you're going to divide it to find the radius. Then They're probably not going to give you the period, and they're not going to give you the frequency. You're probably going to have to solve for period yourself. Then you can actually go ahead and do the equation. What I'm trying to say or get here at to you is that there's a good chance that you're going to have the multiple step questions is what I'm trying to say. Multiple steps. So just be prepared for those multiple steps. Let's keep going.
And the next one they had for you.
What's the radius?
10,
She says it's 10
right?
because the track is across, so now it's going to be 10 meters, not 20 meters. They gave us 5 laps is the amount of turns, 60 seconds is the time.
12?
So my radius is, I agree with Emilia, 10 meters. The period, though, is the amount of time divided by turns. So you got 60, Emilia, divided by 5.
Yep.
And what'd you get?
12 something.
I agree with her. Now the tangent velocity, we're going to go ahead and use number 7 again. VT equals 2 pi r over capital T, or 2 pi 10 over 12.
Which I got 5.23 meters per second.
And that's what I got too. So not too bad.
Do you
Not
want-
too bad because we're doing step by step by step. But come quiz day, they're just going to ask you this question and they're not going to give you step by step. You need to be able to know that you're going to have to do step by step. I'm listening.
Do you want us to take it to the hundredths where
I-
it is,
to-
or do
to-
you want us to take it to the thousand?
Can we do it 2 places to the hundredths? If we can do it to the hundredths.
Would you prefer more, or?
No. I go to the hundredths because pi goes to the hundredths, 3.14. I understand pi goes like infinity, but we traditionally use it at the hundredths, 3.14, if that makes sense. Couple of more just to make sure. Number 3 actually uses a different equation. It doesn't use the first equation. It says here that there's a child that's on an ice cream parlor stool that spins. The child turns counterclockwise. Okay. Changing the displacement of his feet 8 rads in 6.3 seconds. What is rads? Rads are going to be theta, right? In physics, theta for circles is rads, not degrees. This is the amount of time it took. Determine the angular speed, omega. So in this case, I'm going to go ahead and use the omega equals theta over t, which 8 divided by 6.3, pretty straightforward, thank goodness. I don't have to do multiple steps. I got 1.27 rads per second. So it's pretty straightforward. The next one. The next one's kind of a 2-step problem here. A car on the Ferris wheel, right, that's rotating around, is 37.94 meters from the center. From the center is radius. As the Ferris wheel spins, the car is going to move in a arc length, lowercase s, of 29.8 meters. Meters is good, so we don't have to convert. In 50 seconds, t for time. Determine the angular speed, omega, of the car on this Ferris wheel. Okay, I'm going to pause and I'm going to go ahead and go backwards to our equations.
Don't we have to find the period first?
Well, could I use this first equation at the top?
You could in a later date.
I could in a later date because I don't have the period, right?
You have to use,
I can use 2 or 3. Could I use 3, the bottom one? No, because I don't have tangent velocity. So I'm going to have to use the second one. But there's a problem. omega equals theta over t. I have t, yes I do. I have r, bless you, and I have arc length, which is lowercase s. So that means that I'm going to have to go backwards to a couple of pages previous, which is equation number 3. And on equation number 3, it actually has what we call angular displacement, and it looks like this. Theta is s over r. So step 1 is theta equals s over r, or 29.8 divided by 37.94. 0.78 is what I got. Rads. That's not my answer. I'm going to now have to go to step 2.
Wait, how did you get 0.78? I got 0.078.
Oh, did you?
Yeah. I got 0.78.
I did
Let
too.
me just double check mine. Okay, no, I was wrong.
Okay.
Got 7.5.
0.75, 0.78. So somewhere's around there. But step 2 now is going to be using the omega equals theta over t, or 0.78 over, they did give me the time of 50 seconds. And my answer is going to be in rads per second.
I got 0.0156.
Sounds good to me. Yep.
What was it?
Yep, I would round it. 0.02. No.
7.2?
What was it, 7.2 or 0.2? 0.2.
Thank you.
Mm-hmm. Okay. So now, I'm done. I'm going to leave one equation for you to practice on this page. I'm going to leave, there's an equation, I think, on a previous page. Now, next week when we come back, let's look at those equations together next week. And next week, you don't have to. And next week when you get back, let's look at homework 1 and homework 2. I do not think centrifugal acceleration's on homework 2 at all. It shouldn't be. So we should be okay and be able to do homework 1, homework 2 when we see each other. Which one?
What about number 2 and number 1? You said W.
You should be able to do every question now, because remember I sent you an email saying, oh, don't do this problem?
And number 7?
Number 7, you should be able to do every question on homework 1 and homework 2. Homework 1 and homework 2. See you on Monday. Homework 1 and homework 2. Every question now.
Bailey video?
Oh, no, what are we doing? Oh, what
It's my heart. It's a
What?
heart. It's half of a heart, and then you add the other half.
She ain't here, so it's broken. Oh. Okay, now.